solve 12 problems from the topic of pure substances. Okay, the first problems here, we have steam at 220 degrees in a rigid tank with a volume of 2 meters cubed. Now, if a quarter of the tank is filled with liquid water, we're asked to find the pressure of the steam, the quality of the steam, and the density of the steam. Okay, so let's draw a simple schematic of the problem first. Now, the word rigid in thermodynamics is usually used to indicate that the volume cannot change. So the volume is going to be constant because this tank is rigid, it cannot expand, it cannot shrink, so the volume does not change. So keep an eye for these keywords. Okay, so we have our tank and its volume is given, 2 meters cubed, and the temperature of steam is 220 degrees Celsius. Now, a very important piece of data that the problem is giving us is that a quarter of the tank is filled with liquid water. So that says the volume occupied by fluid is 1/4 of the total volume, right? So we can start to plug in numbers. Now the volume is 1/4 of the total volume, which is 2 meters cubed. So we get that 0.5 meters cubed is filled with liquid water, right? So this should immediately give us a hint. Now we have 220 degrees Celsius steam in a tank, and only 1/4 of the tank is filled with water. So the rest is filled with vapor. So what this information gives us is that liquid and vapor are coexisting in the same tank. So that means that we are dealing with a saturated mixture. Now, because we're dealing with a saturated mixture, we know that temperature and pressure are related to each other. So the pressure of the tank is equal to the saturation temperature at 220 degrees Celsius, which, if you go check the tables, is 2319.6 kilopascals. So there we have it. This is part A. Now, for those of you who are wondering, I'm using the steam tables provided in Chengel's thermodynamics book. I have found a link to these tables. I've shared the link in the descriptions down below. So if you don't have access to any property tables, at least for water, make sure to check the link out. Okay, I just cleared a bit of the calculation area, so we can continue to part B. Now, part B asks for the quality of steam. So here in this scenario, I think we can go and find the mass of the vapor and the mass of the fluid directly. Let me show you how. So we already concluded that we are in a saturated mix, right? So we can go and read the tables for saturated mixture at a temperature of 220 degrees Celsius. So if we do that, we get that the specific volume of the saturated liquid is 0.00119, and the specific volume for saturated vapor is 0.086094. Both of them in meters cubed per kilogram, right? Okay, what else do we know? We know that the volume that the fluid is taking is 0.5 meters cubed, right? So if this equation is true, then I can say the mass of the fluid or liquid is the volume of the liquid divided by specific volume, the saturated liquid. Now plug in some numbers in that equation, I get mass of the fluid or the liquid is 0.5 over 0.00119. If we do the calculations, gives us 420.19 kilograms. So we have this much mass in liquid water. Now, how about the mass of vapor? For vapor, 0.5 meters cubed of this tank is filled with liquid. The rest is filled with vapor, right? So the volume that the vapor is taking is equal to 2 meters cubed minus 0.5 meters cubed, which is 1.5 meters cubed. Again, we are going to use the equation that the volume is equal to mass of vapor times the specific volume of vapor. Now plug in numbers and you get mass of vapor is equal to 1.5 over 0.086094, which gives us a mass of 17.42 kilograms. All right, so now we have the mass of both liquid and the vapor. Okay, so I cleared up the calculation space again, and here's the mass of vapor, and here's the mass of the fluid. So quality, we define it as the mass of vapor over the total mass of our system, right? That will be 17.42 over 420.19 plus 17.42. Now, if we do the calculations, for the quality is roughly 4%. Now, for part C, we are asked to find the density. Now, the density of a system is the mass of the system, total mass of the system, over the total volume of the system. Now, the total mass is 420.19 liquid plus 17.42 steam over the volume, which is given 2 meters cubed. Now, do the math, and we get that the density is 218.795 kilograms per meters cubed. All right, problem 2. Let's take a look at our problem. I'm going to draw a schematic. So we have this system. This is the piston, and we have water inside. Outside air, or the atmosphere pressure, is 100 kilopascals, and this piston itself is 20 kilograms. Now, what is the pressure that the water is feeling? So let's call it pressure of water, PW. Now, if I draw the free body diagram of that piston, what I get is, this is my piston. The forces acting on it are the pressure of the water times the cross-section area of the piston acting upward, the pressure of atmosphere times the cross-section area of the piston acting downward, and the weight of the piston also acting downward, right? So we are heating this system up gradually, so we are looking at a constant pressure process. So the summation of forces in y direction, the summation of all these pressures, should be 0. If that's the case, then I'm going to say the forces in y direction should be 0. I'm going to conclude that the pressure that the water is feeling is equal to atmospheric pressure plus the weight of the piston over cross-section area. I just did an algebra and played with the cross-section area in this equation. Now we can plug in some numbers. So the pressure will be 100 kilopascals. I am going to change the kilopascals into pascals. So we are looking at 100 times 10 to 3 pascals plus. Now, the weight of the piston is mass times gravitational acceleration. For simplicity, I'm going to take G, the gravitational acceleration, in SI units at 10. So the mass is 20 times 10 over the area. Now, area is 100 centimeters squared, right? I'm going to convert it to meters squared. In order to do that, I'm going to say 1 centimeter is 0.01 meters. So 1 centimeter squared is 0.0001 meters squared. Now we have 100 of them. So 100 times 10 minus 4 meters squared, right? If we do the math, we get 100 times 10 to 3 plus 20 times 10 to 3, which is 120 times 10 to 3 pascals for 120 kilopascals. Now, the reason that I changed the unit of atmospheric pressure to pascals in the beginning was that this equation over here will give you pascals. So in order to be able to add these two numbers together, you have to have them in the same unit, which is pascal. Now that the result is 120 times 10 to 3 pascals, I can make it back to kilopascals, which is 120 kilopascals. So this is a constant pressure process, and we found the pressure of water. Now, the moment that water starts to boil corresponds to when the water reaches the saturation temperature at this pressure. We need to go and check the tables to find the set temperature. Now, the tables that I have provided in the link below do not have the properties of water at 120 kilopascals. What they do have is the properties at 100 kilopascals and the properties at 125 kilopascals. So we need to do a linear interpolation to find the saturation temperature. Okay, I cleared the calculation area, and I'm going to show you how to do linear interpolation with the data in these tables. It's a very handy tool to get familiar with because linear interpolation often happens with these kind of tables. We end up with a certain temperature or with certain pressure that are not in the tables, and we need to do linear interpolation. Okay, so what I want to find is the saturation temperature. I'm going to check the table. I can see that for pressure of 100 kilopascals, the saturation temperature is given at 99.61 degrees Celsius. For pressure of 125 kilopascals, however, the saturation temperature is 105.97. We are looking for the pressure of 120. Assume that we have a TT space like this, or rather TP space like this. Then I'm going to say, hey, at 100 kilopascals, the temperature was 99.61. Then I'm going to say, hey, at pressure of 125, the temperature was 105.97. And I'm looking for the pressure 120. I want to find the temperature of 120 kilopascals. So what I'm going to assume is that between these 2 points that I know, I can draw a straight line. And then I can find the temperature using this line. Now, all we need to do is find the equation for this green line. So let's get to it. I can say T minus 99.61 over P minus 100 is equal to 105.97 minus 99.1 over 125 minus 100. So all I did was trying to find the equation of this green line using the slope and one single point. Now I'm using this point over here and also using the slope of this line. Okay, so if we continue with this, we can get that temperature is 0.2544 times pressure minus 100 plus 99.61. So this is the equation of our green line, right? I'm going to plug in 120 as my P and find the temperature. Okay, I plugged in the numbers and found that our temperature is 104.698 degrees Celsius. Now, in order to check your answer, let's go back to our table here. We are doing a linear interpolation, so the data that we get should be larger than our lower bound and smaller than our higher bound. Now 104.698 fits that criteria, so we are kind of sure that what we did was right, and this is the actual temperature. So in order to answer this question, the temperature at which the water starts to boil, that will be 104.698 degrees Celsius. Okay, problem 3. So we have a rigid tank with a volume of 2 meters cubed. We have a saturated mixture at 75 degrees, and the mass of this mixture is also given 20 kilograms. And we are going to heat this mixture up until the liquid is completely vaporized. Find the temperature and also show the entire process on a TV diagram. Okay, so first let's draw a schematic of our problem. This is our tank, and 2 meters cubed, we have 20 kilograms, and also the temperature is given. And we also know that it's a mixture at initial state. So the problem asks to show the process on a TV diagram. So let's start with that. I'm going to draw a TV diagram like here. This is T in degrees Celsius, and this is V in meters cubed per kilograms. And this is our dome. So initially, we know that our temperature initially is 75 degrees Celsius. Now, we know where on y-axis or t-axis we are. We need to find where on x-axis or specific volume axis we are. So let's get started on that. Specific volume is the volume. I'm going to put 1 here to show that we are talking about the initial state. Is volume over the mass. So we have 2 meters cubed over 20 kilograms, which is 0.1 meters cubed over kilogram. So I'm going to end up somewhere like here, maybe. So this is our initial state, 0.1. Now we're going to heat up this mixture. Now the thing that we need to pay attention to is that we need to know what kind of process we are dealing with. Again, we are talking about a rigid tank. A rigid tank means that the volume remains constant. Now, if volume remains constant, if the mass is constant again, no mass is entering or exiting our system, then the specific volume will be constant as well. So I know that the second specific volume, or our final specific volume, is also 0.1. I need one more piece of information about our second state so that I can pinpoint it on this diagram. Now, the problem says that the liquid is completely vaporized. Now, when the liquid is completely vaporized, it means that we are dealing with a saturated vapor scenario. So that is the second piece of information that we need. This line over here, this line right of the critical point on the dome shows the saturated vapor, right? This is saturated vapor line. And we are dealing with the constant volume problem. So the constant volume means the volume remains the same. We are going to hit it on the saturated vapor line right there. So this is the second state, or the final state. Okay, so I'm going to check the tables to see at what saturation temperature the specific volume for saturated vapor is equal to 0.1 meters cubed per kilogram, which is our specific volume at final state. Now, if you do that, you will see that around the temperature of 210 degrees Celsius, the specific volume of saturated vapor is very close to 0.1. If you check table A4, you will see that the specific volume that we have, 0.01, is actually smaller than the specific volume of saturated vapor at 210 degrees, but it's very close to the value. Now, if you want to be super exact, you can do a linear interpolation between 210 degrees and 215 degrees Celsius to find the saturation temperature. Okay, so we have a piston cylinder that is having water at 40 degrees with a pressure of 200 kilopascals, and the initial volume is also given, 50 liters, and we are going to heat this water in a constant pressure process until the entire liquid is vaporized. Now, if that's the case, we are asked to find the mass of the water, the final temperature, the total change of enthalpy, and also show the process on a TV diagram. So a few keywords that we need to pay attention to. So again, we see this phrase, the entire liquid is vaporized. This means that our final state is actually saturated vapor. We also have a keyword here, the process is constant pressure. We need to first know the state of our system at the initial phase. We have the water at 40 degrees and the pressure is also given. How do we do that? Easiest way is go check the tables. So check the tables and see what is the saturation temperature at P equal 200 kilopascals. Now, if you do that, you will see that the saturation temperature is 120.21 degrees Celsius. Now, our initial temperature, T1, is 40 degrees, which is way smaller than the saturation temperature at the set pressure. We are dealing with a compressed liquid. Now, if you're confused on how I figured this out, I'm going to show it on a TV diagram in a second. So if this is our TV diagram, this is T and this is volume, and this is our famous dome, then I need to find the constant pressure lines, which is this. And in the case of our problem, this constant pressure line is 200 kilopascals. Again, we checked the tables and found out that the saturation temperature is 120 degrees Celsius, right? But our initial temperature is 40. So we are looking at 40. Now, if we do the drawing here on the diagram, you will see that we ended up on the left-hand side of the saturation dome, which means we are in the compressed liquid space. Now we can use this to find the specific volume of our system at the initial state. Now remember, for compressed liquid, we usually don't have access to property tables. What we can do is approximate the properties at this temperature with the properties of the saturated liquid at the same temperature. So I'm going to assume that the properties of the green point, which is our initial state, are equal to the properties of the black point, which is the saturated liquid at 40 degrees Celsius. Now I'm going to check the tables to find the specific volume here. Now, if we do, we find that the specific volume of the black point is 0.001008 meters cubed per kilogram. Okay, now that we know the specific volume at state 1, we can find the mass. So for part A, I know that the mass is volume over the specific volume, right? So that will be 50 liters, which is 50 times 10 minus 3 meters cubed over 0.001008. And if we do the math, we get that the mass is 49.6 kilograms. So nearly 50 kilograms of water is in this piston and cylinder setup. Okay, I cleared a bit of the calculation space, so we can move on to part B. Now for part B, it asks for the final temperature. Now, we need to know what the final state is. That's when this part of the problem gets important. We are dealing with a saturated vapor at the second state. We also know that the process is constant pressure, right? So we are following the constant pressure line like this until we hit the saturated vapor scenario, right? So this is our second or final state. Now the temperature of this second state, we already checked with the tables, is the saturation temperature of 200 kilopascals pressure, which is 120.21 degrees Celsius. Easy peasy. Okay, for part C, we are asked to find the total enthalpy change. Now, when you see the total enthalpy or total internal energy or anything with the word total behind it, it means that we are talking about the extensive property. So we are asked to find the change of capital letter H. Now, the change of capital letter H for our case is the mass of the system times the change of small letter h, right? Now, we need to find the values of H2 and H1. H2 is the enthalpy of the final state. Now, we already know that the final state is saturated liquid. So check the table and find the value of saturated vapor at P equals to 200 kilopascals. For H1, on the other hand, we need to do some sort of approximation again. Now, all of the properties of a compressed liquid can be approximated with the properties of the saturated liquid at the same temperature, except for enthalpy. Enthalpy, if you remember, is the internal energy plus pressure times a specific volume. Now, because it has a pressure term, this approximation, this easy approximation that, hey, whatever compressed liquid we're looking for is the saturated liquid, does not work with enthalpy. So we are given an equation to some extent accurately approximate the enthalpy of a compressed liquid. So H of our compressed liquid is equal to H of the saturated liquid at the temperature that we have, in this case is 40 degrees Celsius, plus the specific volume of the saturated liquid at the same temperature, times the pressure of our compressed liquid minus the saturated pressure of that temperature. So I'm just going to plug in some numbers from the tables. The enthalpy of a saturated liquid at 40 degrees Celsius is 167.53 plus the specific volume is 0.01008 times the pressure that we have is 200 kilopascals minus the saturation pressure at temperature of 40 degrees is 7.3851 kilopascals. Now, if we do the calculations, we get that the H, or enthalpy of initial state, is 167.72 kilojoules per kilogram. Again, I cleared up the space, and let's plug in some numbers. So, change of capital enthalpy is equal to the mass. We already know that it's 49.6 kilograms. H2 was the enthalpy of saturated vapor at 200 kilopascals, which is 2706.3, minus H1 we found is 16.772. And if we do the calculations, we get that the change of enthalpy is 125,913.36 kilojoules. Now for part D, it asks to show the process on a TV diagram. We kind of already did. So the process is the red line, and the direction is from point 1 here, the green dot, all the way to point 2 here, the red dot. Let's continue with problem 5. We have a rigid tank, the volume is given, and we have a mixture of saturated liquid and vapor at 150 degrees Celsius. We are going to heat this system up until the water inside reaches the critical state. We are asked to find the mass of water and also the volume occupied by the liquid phase initially. Okay, so what do we know about the initial state? Remember, we always need two independent intensive properties to be able to fully express the state of a system. Now here, all we know is that initially it was 150 degrees. We also know that it was a saturated mixture, but we don't know where between saturated liquid and saturated vapor. In this case, we know more about the final state than the initial state. We already know that the final state is at critical point, and we have the data for water at critical state. What else do we know? There is a keyword that we have seen a lot in this video, and that is tank being rigid. Now, a rigid tank means that the volume is constant. So we know that the process from initial state to final state is a constant volume one. So let's draw the process on a TV diagram to see what we can get out of all that we know. So this is our TV diagram, and this is our dome. Initially, the system was at 150. Now we know that the final state, or the second state, is here, the critical point. And we also know that the process from initial state to our final state is constant volume. So this red line is actually the process, right? Where this red line crosses the purple line is where our initial state is. So we found the initial state. Because the volume has been constant, we know that the specific volume at the initial state is equal to the specific volume at critical state, which we already know is 0.003106 meters cubed per kilogram. Okay, so in order to answer part A, we can say, check the table for 150 degrees Celsius, and we get that the specific volume of saturated liquid at that temperature is 0.001091, and the specific volume of saturated vapor is 0.39248, both of them in meters cubed or kilogram. Now we know that our specific volume is 1 minus the quality initially, or the quality of the initial phase, times specific volume of saturated liquid plus quality times specific volume of saturated vapor. Now I'm going to play with the equation to find quality. That will be specific volume minus specific volume of saturated liquid over a specific volume of saturated vapor minus specific volume of saturated liquid. Now plug in the numbers that we have. We get 0.00316 minus 0.001091 over 0.39248 minus 0.001091, and do the calculation. We get quality is 0.005, or in other words, it is 0.5%. So we found the quality. Now let's use that to find the actual mass. Okay, I cleared up the calculation space so we can proceed with our solution. First, let's find the total mass of water in this rigid tank. So that is easy. We know that the total mass is the volume of the tank over the specific volume of our system. Now, the specific volume of the system, we already know, is the specific volume of critical water. So 0.3 meters cubed over 0.03106 meters cubed per kilogram gives you about 96.6 kilograms of total mass of water. But we are interested in the mass of the fluid. So I'm going to say mass of the fluid is the total mass minus the mass of the vapor. If I divide both sides by the total mass, I get mass of liquid over total mass is 1 minus quality. So I can play with this and say mass of the fluid is actually total mass times 1 minus quality. So plug in numbers, I get the fluid mass, or the liquid mass, is 96.6 times 1 minus 0.005, which, if you do the calculations, gives you mass of the liquid is 91.77 kilograms. Okay, to continue to part B, we are asked to find the volume occupied by the liquid phase. So that is actually very easy. Remember that when we checked the tables, we found that at 150 degrees Celsius, the specific volume of saturated liquid is 0.01091 meters cubed per kilogram, right? So the volume that the liquid is occupying is the mass of the liquid times the specific volume of saturated liquid. So plug in numbers, we get 91.77 times 001091, and the final number is about 0.1 meters cubed. So 1/3 of this tank was initially filled with liquid water. Okay, problem 6. This time we are dealing with a constant pressure situation. 1.2 kilograms of steam, the temperature and the pressure is given, is cooling down in a constant pressure process until 1/2 of the mass condenses. Okay, so this is one key piece of information that the problem is giving us. Now, we are asked to find a bunch of things. First, show the process on a TV diagram, then find the final temperature, and then find the volume change, the total volume change. Now, let's start with part A. So this is my TV diagram. And this is my dome, right? We know that initially the temperature is 300 degrees Celsius and the pressure is 1 megapascal. So first of all, let's find the 1 megapascal pressure line. So this is, let's say, the 1 megapascal pressure line. And the temperature is 300. We need to first figure out where on this line we are. Okay, so in order to do that, it's actually rather easy. We're going to check the tables for 300 degrees. Okay, now if you do that, you will see that the saturation pressure for the temperature of 300 degrees Celsius is 8.58 megapascals. Our initial pressure, which was 1 megapascals, is way smaller than the saturation pressure at 300 degrees Celsius, right? So what does that mean? It means that we are dealing with a superheated vapor. I'm going to show it on the TV diagram here. So if the red line is showing the constant pressure of 8.58 megapascals, you can see that the temperature of 300 degrees crosses the purple line of 1 megapascal here on this green dot. Because we ended up on the right-hand side of the dome, we are in the superheated region. Now, what do we know about the process? We know that the process happens in a constant pressure, and we also know that the final state, half of the mass has condensed. Now, when half of a mass is condensed, it means that the other half is still in vapor form, right? So it means that our final state is a saturated mixture somewhere in the dome. Now we need to find where. So this green dot in the middle is our final state. We also know the quality is 0.5 because the problem explicitly says that half of the mass is in the liquid form. Now, in order to answer part A, showing the process on a TV diagram, this green line coming from 1 to 2 is the process. Now, for part B, we need to find the final temperature, right? Now, we concluded that the second state is a saturated mixture. In a saturated mixture, the temperature is a function of the saturated pressure, which in our case is 1 megapascals, and so the saturation temperature from the tables is 179.88 degrees Celsius. For part C, we are asked to find the change of total volume, which is mass times the change of specific volume. Now we need to find specific volume at final state and specific volume at initial state. So at the initial state, we were at superheated region. So we can go to the superheated vapor table and read the specific volume at 1 megapascals and 300 degrees Celsius, which is 0.25799 meters cubed per kilogram. At state 2, because we are in a saturated mixture, we need to use the quality. So we are going to go check the tables and read the specific volume of saturated vapor and liquid at 1 megapascals pressure. So specific volume of saturated liquid at 1 megapascals of pressure is 0.001127, and the specific volume of saturated vapor is 0.19436, both in meters cubed per kilogram. Okay, the specific volume of final state is 1 minus quality times specific volume of saturated liquid plus the quality times the specific volume of saturated vapor. Plug in the numbers that we have, and doing the math, we get that the specific volume at final state is 0.097743 meters cubed per kilogram. Okay, now we have both specific volumes. We can plug in back into our equation. Change of total volume is mass 1.2 times 0.25799 minus 0.097743, which will give us a change of volume of 0.1923 meters cubed. Okay, let's continue to problem 7. So we have 1.4 kilograms of saturated liquid at 200 degrees, and this liquid is filling up a quarter of a rigid tank. Now the rest of the tank is filled with air. Now we are going to heat this container until all of the water has turned into saturated vapor. Now we are asked to find the volume of the tank, the final temperature and the pressure of our system, and the change of internal energy during this process. So let's start with drawing a schematic of our problem. So this is our rigid tank, and a quarter of it initially is filled with saturated liquid, right? 1.4 kilograms, and the temperature initially is 200. Now the problem specifically states that we are dealing with saturated liquid at 200 degrees. So I can go check the tables. So if I go and check the tables, I can see that for 200 degrees Celsius, the saturated liquid has a specific volume of 0.01157 meters cubed per kilogram. Now I know that the volume is mass times specific volume. So the volume of the water is the mass of the water, 1.4, times the specific volume that we have here, 0.01157, which will give us 0.016198 meters cubed. So this is the volume of our saturated liquid. Now, the volume of the tank, so let's go for part A. The volume of the tank is 4 times the volume of the saturated liquid, right? This is what the problem says. The problem says that the liquid is only taking a quarter of the volume. So the volume for the tank is 4 times 0.016,198, which is 0.064,792 meters cubed. So this is our tank. It's about 6.5 liters. Okay, for part B, I again cleared the calculation space. For part B, we are asked to find the final temperature and the pressure of the water. But what do we know about the final state? We know that at final state, we are dealing with saturated vapor only. We also know that we are dealing with a rigid tank. So the volume of the tank has not changed, and we can use that to our advantage. So the specific volume at the final state is the volume of the tank, because the entire tank is now filled with saturated vapor. So the volume of the tank over the total mass, which is 1.4 kilograms, because no mass has entered or exited this rigid tank. So if you plug in numbers, the volume we already know from part A, and the mass is 1.4, we get that the specific volume at final state is 0.04628 meters cubed per kilogram. We know that the final state is saturated vapor. So I'm going to check the table to see at what temperature the saturated vapor specific volume is equal to 0.004628. Now, if we go and check the tables, we will see that at the temperature of 370, the specific volume for saturated vapor is 0.04953, and at 373.95, which is the critical state for water, the specific volume is 0.0031106. Now, the specific volume that we have, this number right here, falls in the middle. So we are here in terms of specific volume, and we are looking for the temperature. You guessed it, we need to do a linear interpolation. I'm not going to do the linear interpolation here because we've already done one example in this video. So I'm just going to write down the final answer. The temperature that we are looking for is 371.3 degrees Celsius. Okay, for part C, we are asked to find the internal energy change of water. So we are looking for delta capital U, which is the mass times small letter u2 minus small letter u1. So at state 1, we know that we were dealing with saturated liquid, right? So u1 is the internal energy of saturated liquid at T equals 200. So I'm going to read it from the tables. That will be 850.46 kilojoules per kilogram. Now for state 2, we know that we are dealing with saturated vapor at a temperature of 371.3 degrees Celsius, right? So we are going to say the U at second state is this internal energy of saturated vapor at 371.3 degrees Celsius. Now, this temperature is not in the table. We found it using the linear interpolation technique. We can use the same technique to find the internal energy. Okay? So if you do that, you will find that U2 is 2,201.5 kilojoules per kilogram. Now delta U will be 1.4 times 2,201.5 minus 850.46, which will give us 1,892 kilojoules. We found the temperature and the internal energy at the second state using linear interpolation. So try to master this technique because, as you can see, we are going to use it quite a lot. A piston cylinder device initially contains steam at 3.5 megapascals and 250 degrees Celsius. Now the steam loses heat and the piston moves down, hitting a set of stops, at which point the cylinder contains saturated liquid water. The cooling continues until the cylinder contains water at 200 degrees. Okay, so what's happening is that we are having a piston and cylinder, something like this. Now there are stops in this piston cylinder system. Now we initially have a situation like this. So this is the initial state. We have 250 degrees and the pressure of 3.5 megapascals. We are going to cool down until the piston hits these stops. So when that happens, we have saturated liquid inside, and then it continues to cool down. Now, because the piston has hit the stops, it cannot go down any further until the water inside is 200 degrees Celsius, right? This is the second state, and this is third and final state. We are asked to find the enthalpy change per unit mass of the steam by the time the piston first hits the stop, and the final pressure and quality if the system is in mixture at point 3. Okay, so for part A, we are actually looking for the change of enthalpy between state 1 and 2. Okay, before we start dealing with the problem, let's first talk about these 3 states and the processes between them. So from 1 to 2, because the piston can freely come down, we are dealing with a constant pressure process. Now from 2 to 3, because the piston is sitting on the stops and cannot shrink any down further, we are dealing with a constant volume process. So this should give us some information. So at state 2, because we had a constant pressure, the second pressure, or the pressure at state 2, is equal to the pressure at initial state. And at the final state, the specific volume is equal to the specific volume of the second state, or the volume of the final state is equal to the volume of the second state. It doesn't matter volume or specific volume. We need to figure out our initial state. So I'm going to draw a TV diagram. This is my 3.5 megapascal pressure line. and we are initially at a temperature of 250 degrees. We need to find our initial state on this line. So let's check the tables. So if we check the tables, we get that the saturation temperature for the pressure of 3.5 megapascals is actually 242.56 degrees Celsius, right? But our current temperature is 250. So our temperature is larger than our saturation temperature, which means we are dealing with a superheated scenario. So saturation temperature was 242, but we are dealing with 250. So here is our initial state, superheated. Now, if I read the table, I get that the initial enthalpy is 2829.7 kilojoules per kilogram. Okay, let's continue to state 2. So what do we know about state 2? We know that its pressure is equal to the first pressure. So we are on the constant pressure line. And we know that we are dealing with saturated liquid. So here is the second state. On the same pressure line, saturated liquid. So I found the second state. This point is saturated liquid. So I can go check the tables, or rather read the tables, and see that our enthalpy is actually the enthalpy of saturated liquid at pressure of 3.5 megapascals, which is 1049.7 kilojoules per kilogram. Okay, I have both the enthalpies. I can find the delta. So delta enthalpy will be H1 minus H2, which will give me 1780 kilojoules per kilogram. So this is the answer to part A. Now for part B, we are asked to find the final pressure and quality if we're dealing with a mixture. So from 2 to 3, we know that the process has been constant volume. So we are moving on this black line because this black line shows the constant volume, right? But where on that black line? So the final state temperature, or T3, is given as 200 degrees Celsius. I'm going to check the tables to find the specific volume of saturated liquid and saturated vapor at 200 degrees Celsius. So specific volume of saturated liquid is 0.001157, and for saturated vapor is 0.12721, both in meters cubed per kilograms. I'm going to check the specific volume at point 3 with these two numbers to see whether we are in compressed liquid or in a mixture zone. But first, I need to find the specific volume at the final state. We already know that it's equal to the specific volume of the second state, and we already know everything about our second state. So specific volume at state 3 is equal to the specific volume at state 2, which is the specific volume of saturated liquid at 3.5 megapascals. And I'm going to use the tables to read it. Now, if you do that, you will see that the specific volume is 0.001235 meters cubed per kilogram. Now, as you can see, our specific volume is between these two numbers, right? It's slightly larger than the specific volume of saturated liquid. just a bit. So we are in a mixture. Now, if we are in a mixture, it automatically gives us the pressure because we already know the temperature. Let me show you. Final temperature is 200 degrees. And if I follow the green line, I hit the black line here. So this is my third state, final state, right, in the mixture. So if I find the saturation pressure for 200 degrees, that will be the final pressure for our system. So I'm going to check the tables. And I'm going to find that P3 is 1554.9 kilopascals or 1.5 megapascals. Okay. Now quality is specific volume 3 minus the specific volume of the liquid, saturated liquid, 0.3 over specific volume of saturated vapor at 0.3 minus a specific volume of saturated liquid at 0.3. And if you plug in numbers, we get that the quality is 3.09 times 10 to minus 4, or quality is about 0.3%. So nearly all of the water is in liquid form. Only 0.03% of our system is in vapor form. All of it is in liquid. And to finish this problem, this green line is the entire process that our system went through. All right, problem 9. Now this one is the most challenging one yet because of a new element in the problem in the form of a linear spring. Okay, so we have a piston and cylinder. It has water inside at 5 megapascals of pressure and 400 degrees Celsius of temperature, and the volume is 0.1 meters cubed. Now, this spring is in a way that when the piston is on the bottom of the cylinder, meaning the volume is 0 and it's like on the bottom, we still experience some sort of pressure in the form of 200 kilopascals acting downwards on the piston. Now we are going to let this system cool down until we reach a final pressure of 1200 kilopascals. We are asked to find the mass of the water in the system and final state, and also show the entire thing on a PV diagram. So let's start with the schematic of the problem. We are dealing with a scenario like this. This is our piston cylinder, and this is our spring, and this is the piston. Initially, we have 5 megapascals and 400 degrees, and the initial volume is 0.1 meters cubed. So first things first, we need to pinpoint the initial state. For that, we are going to check tables. I'm going to check the saturation temperature for the pressure of 5 megapascals. Now, if we check the tables, it's 263.94 degrees Celsius. Now, the temperature that we have initially is 400 degrees, which is greater than the saturation temperature, which is 263.94. Now, you know this means that we are dealing with a superheated vapor. Now, in order to find the mass of the system, we need to take a look at what we have. We already know the total volume. It's 0.1. Now, if we know the specific volume of our system at state 1, then we can use the equation mass is volume over specific volume, right? So let's do that. If I go and check the tables for the superheated vapor at 5 megapascals and 400 degrees, I would see that the specific volume is 0.05784 meters cubed kilograms. Okay, now I can plug in numbers here. Mass is 0.1 over 0.05784, which is 1.728 kilograms. So that's it. We found the mass using the volume, the total volume of the system initially, and the specific volume of the system initially. Okay, for part B, we first need to know what do we know about the final state. What we know is that the final state has a pressure of 1200 kilopascals, right? But that's it. We need to know another piece of information. Now here's where that spring comes into the picture. Let me show what I mean by drawing the PV diagram. So if this is our PV diagram, this is P, this is V, this is the dome, and you know that constant temperature lines are like this, and this is the 400 degrees line. Initially, we had 5 megapascals of pressure, and we were in the superheated region, so we were somewhere around maybe here. So this is our initial state, right? Now the process of cooling down is related to the spring, how I'm going to show you. Remember that the force of a spring has a linear relationship with delta x, or how much the spring has been compressed or elongated. So if the piston during the cooling down gets to this green position, then the force of the spring changes according to this delta x, right? Now that delta x is actually the change of volume of the system over the cross-section area of the piston, right? So this is the area of the piston. So from these two, I can conclude that the force of the spring has a linear relationship with the change of volume. Now we know that the pressure is force over the area of the piston, right? So again, I can conclude that the pressure that the system is subjected to has a linear relation with the change of volume. So this is it. When you see a setup, especially piston and cylinders, that are loaded with linear springs, they are cooling down, they are heating up, whatever is happening, you need to note this point. When dealing with springs, the processes have a linear relation between pressure and volume. So if I want to draw the process line on my PV diagram, as I said, they have a linear relationship. So I'm just going to draw a straight line. Now for drawing a straight line, you either need a point and the slope of the line or 2 points, right? So the first point is the initial state, this red dot. The second point is actually given in the problem. It says when the piston is on the bottom, is at the bottom, the spring exerts a force such that P is 200 kilopascals. So when we are here in the origin of this, where specific volume is 0, pressure is still 200 kilopascals. These are the 2 points on the line of our cooling down process. So I found the black line, which is the process line. All I need to do is find the equation for this line. So let's do that. I'm going to change the 200 kilopascals at the origin to 0.2 megapascals, just so that the units are consistent. So P minus 0.2 megapascals over specific volume minus 0, because at the origin, the piston is at the bottom, there is no volume. is equal to 5 megapascals minus 0.2. I'm trying to figure out the slope. And 0.05789 minus 0. Now from this, we get that pressure in megapascals is 82.91 specific volume plus 0.2. So I found the equation of this black line. Now at state 2, we know that the pressure is 1200 kilopascals or 1.2 megapascals. If I plug in the pressure in our equation, we can find the specific volume at state 2. Let's do that. Okay, so I cleaned up the calculation space. I'm going to say P is 1.2 megapascals. Plug it in this equation and find the specific volume. So specific volume at state 2, if we plug in the numbers in, is 0.012 meters cubed per kilogram. There, we found our specific volume at the second state. Okay, we have the pressure at the second state, we have the specific volume at the second state, so according to state postulate, we can pinpoint our final state. I'm going to check the tables for the pressure of 1200 kilopascals and see what the specific volume of saturated liquid and saturated vapor are. So the specific volume of saturated vapor is 0.001138. The specific volume for saturated vapor is 0.16326, both in meters cubed per kilogram. Now our number is somewhere between the saturated liquid and saturated vapor. We are somewhere in between here. So that means we are in the saturated mixture zone. The saturation temperature for 1200 kilopascals is 187.96 degrees Celsius. And the red line on the PV diagram is the constant temperature of 187.96. And where the black line and the red line collide is our second state. So our second state, in order to answer part B, is a saturation mixture. And for part C, to show the entire process on a PV diagram, the entire process is this green line, cooling down from point 1 to point 2. Please pay attention that when dealing with linear springs, during the process, pressure has a linear dependency on volume. That's why we have to draw this black line, and then we continue to find the linear equation between the pressure and volume. Okay, let's move on to problem 10. This is our first problem dealing with the ideal gas equation. So we have again a rigid tank that we have an ideal gas in at a temperature of 600 kelvins and 300 kilopascals. Now, during the process, half of the gas is withdrawn from the tank. At the final state, the pressure of the gas is 100 kilopascals. We are asked to find the final temperature, and then we are asked to find the final pressure if the process was different and no mass was withdrawn, but the final temperature was the same. Let's start with part A. What do we know? We know that at the initial state, P1 is 300 kilopascals, and temperature is also 600 Kelvin. Now, please pay attention that when using the ideal gas equation, you always need to plug in temperatures in Kelvin units, okay? And the mass is M1. We don't know how much mass we have, but we know that it's M1. This was initially. Now, finally, at state 2, we have the pressure, which is 100 kilopascals. We don't know the temperature. And we know that the second state or final state mass is half the initial mass. Now, this is important. So ideal gas equation says that pressure, a specific volume, over temperature is equal to gas constant, right? We also know that the specific volume is actually volume, the total volume, over the mass of the system. If I combine these two equations, I get pressure, total volume, over temperature times mass is equal to gas constant, right? So this is the equation that we are going to use. At state 1, pressure 1, volume 1, over temperature 1, mass 1 was equal to gas constant. At state 2, pressure 2, volume 2, over temperature 2, mass 2 is equal to R. Now, the right-hand side of both of these equations are the same, so I can conclude that pressure 1, volume 1, over temperature 1, mass 1 is equal to pressure 2, volume 2, over temperature 2, mass 2, right? Now, we are talking about a rigid tank. Remember, the rigid tank means that the total volume remains constant during the process. So, immediately we can conclude that volume 1 is equal to volume 2. So, volume 1 and volume 2 can be crossed off from both sides of this equation. We also know that M2 is M1 over 2. So, I'm going to replace that here. M1 over 2, and then I can cross the M1s. So I end up with this equation. Temperature 2 is pressure 2 over pressure 1 times temperature 1 times 2. Now plug in numbers. I get temperature 2 is 100 kilopascals over 300 kilopascals times 600 times 2, which will give us 400 Kelvin. All right, so this is how we tackled the problem. We used the ideal gas equation and the fact that pressure times the specific volume over temperature is always equal to the gas constant, regardless of the process. So we manipulated the equation and used all the keywords that were given in the problem. Rigid tank, meaning that the volume is the same between the two states, and that the mass of the second state is half of the mass of the initial state. So we answered part A, 400 degrees Kelvin. Okay, so for part B, we are asked to find the final pressure if the final temperature is the same, which is 400 degrees Kelvin that we just found out, and no mass has been withdrawn. So the second mass is actually equal to first mass. So again, we're going to use the ideal gas equation. Now this time, because the mass has not changed, it means that the specific volume at the initial and final states are the same, because both volumes are the same and both masses are the same. So specific volumes are the same. Now I'm going to say initial pressure, specific volume over initial temperature is final pressure, specific volume over the final temperature. Now specific volumes are the same, so these go out. And so this equation reduces to second pressure is T2 over T1 times P1. Now plug in numbers, you get P2 is 400 kelvins over 600 kelvins times 300 kilopascals. So P2 is actually 200 kilopascals. So if no mass exits the system during this alternative process, our final pressure will be 200 kilopascals. Okay, problem 11. We have two rigid tanks that are connected with a valve. We are keeping hydrogen in both tanks. The properties of hydrogen at either tank is given. Now we open the valve and let the hydrogens mix, and then let the system reach thermal equilibrium with the outside air. And then we want to know the final pressure in the tanks. So let's draw a schematic of the problem first. So this is tank A. This is the valve. And this is tank B. So initially, in tank A, we had hydrogen with a temperature of 20 degrees and a pressure of 600 kilopascals. In tank B, we had hydrogen with a temperature of 30 degrees and a pressure of 150 kilopascals. Okay, so the ideal gas is still usable here. We know that pressure, specific volume over temperature is equal to gas constant. So at the final state, after the valve is open and both tanks have mixed and reached the equilibrium with outside air with the temperature of 15 degrees Celsius, what is the final pressure? So my final pressure is the hydrogen gas constant times the temperature T2 over the specific volume V2. Now I know what T2 is. T2 or T final is 15 degrees Celsius, which is 288 Kelvin. Remember that Kelvin temperature is Celsius temperature plus 273. Okay, so I know that second temperature. The gas constant, I know it from the tables. P is the one I'm looking for. What about specific volume at the final state? Now, the specific volume is the total volume over total mass. Now at final state, where the valve is opened, the total volume is the volume of tank A plus the volume of tank B. And the total mass, again, is the mass of tank A plus the mass of tank B, hydrogen in tank A and hydrogen in tank B. Now the problem says both tanks are rigid and they have the volume of 0.5 meters cubed. So both volumes are 0.5 meters cubed. Now how about the masses? Masses are the one that we need to calculate. So let's go back to initial state of tank A. So for tank A, again, the ideal gas equation is valid. I'm going to say pressure A times the specific volume A over temperature A is equal to hydrogen gas constant. Now from the tables, hydrogen gas constant is 4.1242 kilojoules per kilogram Kelvin. Okay, I'm going to plug in some numbers. The pressure is 600. Specific volume is unknown. Temperature is 20 degrees Celsius. Using the equation, the conversion equation up here, we know that it's 293 degrees Kelvin, and it's equal to 4.1242. Now doing the math, specific volume of tank A is 2.01 meters cubed per kilogram. Now, using the equation that mass is volume over specific volume, I can get that mass of hydrogen in tank A is 0.25 kilograms. So 0.25 kilogram of hydrogen is in tank A. We need to do the same thing for tank B. So this time for tank B, again, PB, specific volume B, temperature B is equal to R. Plug in numbers, 150 kilopascals, specific volume B, over 30 degrees Celsius, which is 303 Kelvin, is 4.1242, which will give us specific volume of tank B is 8.33 meters cubed per kilogram. Now, using the equation mass is volume over specific volume, we get that the mass of hydrogen in tank B is 0.06 kilogram. 0.06 kilograms of hydrogen is in tank B. Okay, now we can find the final specific volume. So V2 is volume of tank A plus the volume of tank B over mass A plus mass B. This will give us 1 over 0.25 plus 0.06, which is 3.22 meters cubed per kilogram. Now we can use this inside the equation up here to find the final pressure. So let's do it. So the final pressure is hydrogen gas constant, final temperature over final specific volume, plug in numbers, 4.1242 times 288 over 3.22. This will give us the final pressure is 368.9 kilopascals. So just to recap, when the valve is opened, the hydrogen gas in tanks A and B get mixed up and they reach a final temperature of 288 Kelvin. We need to find a specific volume at this final state in order to be able to use the ideal gas equation. So we backtracked to the initial state of each tank and found the mass, and then used those masses and the volume, the final volume of our equilibrium state to find the specific volume at final state, and then plugged everything into our ideal gas equation and found that the second pressure, or the final pressure, is 368.9 kilopascals. Okay, the final problem of today. So we are talking about a tire, automobile tire. It says that when the air temperature is 25 degrees Celsius, the gauge pressure inside the tire is 210 kilopascal. Okay, now the volume of the tire is given. It says when the temperature reaches 50 degrees Celsius, what is the pressure inside the tire? And how much air we need to bleed off in order to restore the pressure. So what do we know from the initial state? So we know at the initial state, when the temperature is 25 degrees Celsius, the gauge pressure is 210. Now remember that in thermodynamics, we work with absolute pressures, not gauge pressures. So the pressure, the initial pressure, is 210 plus another 100, in order to convert it back to absolute pressure, is 310 kilopascals. Now at final state, the temperature is 50 degrees Celsius, and we are asked to find the final pressure. PV over T at state 1 is equal to PV over T at state 2, right? Now, initially, the volume of the tire does not change. It's 0.025 meters cubed, and no air has been bled off, so the mass has not changed, meaning that specific volume at state 1 is equal to specific volume at state 2. So if we use that, we can cross the specific volumes from both sides of this equation and write that final pressure is final temperature over initial temperature times the initial pressure. Plug in numbers and make sure to convert the Celsius degrees to Kelvin. We get 323 Kelvin over 298 Kelvin times 310 kilopascals, which will give us 336 kilopascals. So the final pressure when the air reaches the temperature of 50 degrees Celsius is 336 kilopascals. Now, we want to restore the pressure to initial pressure. How much air do we need to bleed off? Now, for the final part of the problem, we want to bleed off some air to restore the pressure to initial pressure. So this final state, I'm going to show it with 3, this new final state. The temperature is going to be 50 degrees, but the desired pressure is going to be 310 kilopascals again. So first, let's start by finding the mass initially. How much air was in the tire to begin with. So I know that P specific volume over temperature equals the gas constant. So I'm going to plug in the initial state information here, 310 kilopascals times the specific volume over the initial temperature, which is 298, is equal to air gas constant. Now for air, gas constant is 0.287 kilojoules per kilogram Kelvin. Plug that here. And then we get specific volume 1 is actually 0.2759 meters cubed per kilogram. Now the volume of the tire is also given. Volume, total volume, is 0.025 meters cubed, right? We can combine these two numbers to find the mass. So the mass of air, M1, is volume over specific volume, which will give us 0.09 kilograms. Okay, I cleared up the calculation space and I'm keeping the mass that we just found up here. Now let's see at final state, if we want to have a temperature of 50 and the pressure of 310, how much mass of air we can have in the tire. So again, T3, specific volume 3, over the final temperature 3 is equal to R. 310 kilopascals times the specific volume 3 over the final temperature of 323 is equal to 0.287. Do the math, we get that specific volume 3 is 0.3 meters cubed per kilogram. Now again, we're going to use the same equation. Mass at the final state is the volume over specific volume, which is 0.025 over 0.3, gives us final mass is 0.083 kilograms. Now the mass that was bleed off, the mass that we need to bleed off, is the difference between the initial mass and the final mass, which is 0.09 minus 0.083, which will give us 0.007 kilograms, or just 7 grams of air. So in order to restore the pressure back to 310 kilopascals, we need to bleed off 7 grams of air. Thank you for staying to the end of yet another video. If you find this video helpful, please give it a like, as it greatly helps the channel. Also, please consider subscribing for more science and engineering content.